It would, I think, be much too large a task to canvass the issues that are under current discussion in this rather amorphous subject known as the philosophy of science. The subject itself has a long history, certainly going back to antiquity, despite the fact that the title philosophy of science is of relatively recent origin. But perhaps instead of plunging right into the midst of some current discussions, it might be worthwhile at least to say a few words on what the subject is. Now, the subject has been variously conceived, and I have no doubt that the content of courses labeled as philosophy of science will probably vary from instructor to instructor. But by and large, it seems to me that philosophy of science directs his attention towards clarifying perhaps 5 sorts of things about science: what the objectives of the scientific enterprise are. I don't mean, of course, any technological or practical objectives or what the social import of science is, but rather what the objectives are from the point of view of establishing something that one might call scientific theory, and to analyze whether the theories offer something that is called an explanation, or whether they simply describe how things happen, issues of this kind, to clarify them and to indicate what is at stake in opting for one rather than another formulation of the goals of the various theoretical sciences. The second focus of attention, I think, is to clarify the nature of scientific knowledge, not by examining some of the stock epistemological issues with which philosophers certainly have also been concerned, but rather to deal with the articulation or the structure of the systems of propositions that constitute the corpus of scientific knowledge, and to see how they're related to each other as well as to matters of more familiar experience. The third focus, I think, is a concern with the general method of science as distinct from the special techniques that science might be employing in the conduct of scientific inquiry, with a view to determining what general rules are tacitly or implicitly involved in the conduct of inquiry, and with a view also to attempting to find some basis or some justification for the rules that are employed. The fourth item is to concern oneself with the nature of the evidence that is deemed to warrant scientific conclusions, and to discuss to what extent it is possible to assign degrees with which one can rationally accept the various conclusions of the sciences. And finally, to examine, to clarify the transformations that take place in the substantive theory, particularly in the light of the philosophical commentary that is often made on developments or revolutions in modes of scientific thinking. Perhaps as an illustration of this last point, I would like to take a minute to read a comment made by Max Born in the preface that he adds to a collection of his essays he published in 1956 called Physics in My Generation, in which he says, and I quote, "In 1921, I believed, and I shared this belief with most of my contemporary physicists, that science produced an objective knowledge of the world, which is governed by deterministic laws. The scientific method seemed to me superior to other, more subjective ways of forming a picture of the world. Philosophy poetry, and religion. Now I believe in none of these things. The border between object and subject has been blurred. Deterministic laws have been replaced by statistical ones. I now regard my former belief in the superiority of science over other forms of human thought and behavior as a self-deception due to youthful enthusiasm over the clarity of scientific thinking as compared with the vagueness of metaphysical systems. I've taken the time to read this because, in a way, the subject I would like to talk about at some length is not unrelated to the attitude which Dr. Bourne expresses in this bit of confession. I may add perhaps that, in my own opinion, a confession of this kind represents what I think is a failure of nerve on the part of a distinguished physicist. But the motivation that lead men to philosophize about science, of course, are various. There might simply be just, if you like, idle curiosity about what is certainly an important enterprise in Western civilization to determine how it achieves what it does achieve. Or it might simply be an interest that might be simply provoked by puzzlement about the relation of current scientific accounts to what one calls common sense beliefs or to previously held scientific beliefs. And it's, I think, of some importance that concern with what, for one reason or other, one calls philosophical questions are of concern not only to the practicing scientist, but they are matters that occupy the minds of some of the outstanding figures in positive science as well, particularly at those periods of scientific development when there appears to be some radical break between old ideas and those that have been recently introduced. And I think it's a fact of history of science that the most vigorous period of philosophical reflection upon the content of and the method of science occur at those points in the development of scientific thought, such as the Newtonian period, the introduction of relatively novel ideas such as those that Faraday and Maxwell proposed, or our own day when there appeared to be such a complete change of attack on many concerns that had appeared to be settled by previous investigators. Now, there are a number of sources of current concern, and one could list them and one could spend many hours indicating what the occasions are for puzzlement or curiosity. Although I will confine myself to just one of these issues, and as a matter of fact to an issue which has been made focal in the physical sciences, there is subject matter for philosophical reflection that is generated by almost every branch of science, by the physical sciences, for example, problems that are raised in attempts to interpret certain currently accepted theories, such as the quantum theory, questions as to whether you're to regard quantum theory in particular as a sort of a black box into which you feed data and pull out other data that you can then put to a test without attempting to give an interpretation to all the intermediate steps, or whether you're to regard the theory as in some sense being an assertion about a world that is not disclosed to common sense experience, or questions about the character of the indeterminism that is postulated by quantum theory, and so on. There's a whole list of specific questions that are raised by present concern, present activity in the physical sciences. Similarly, in biology, some of these problems, of course, have a rather long history, such as the mechanism vitalism controversy, although it take on new forms in the light of substantive advances. But in addition to this well-chewed bit of material, I think there is an important question that philosophers of science should address themselves to if they are interested, as many of us are, in the character of explanatory theories to determine exactly what kind of a theory current evolutionary theory is. Because though some writers have rejected evolutionary theory as really not being a theory on the ground that it offers no predictions whatsoever, whether this claim is right or not, of course, is not a matter that I want to settle by simply making a dogmatic statement, but to formulate, analyze the structure of evolutionary theory, its combination of a number of historical laws with various sorts of statistical assumptions as part of the theory itself, I think offer a very genuine challenge to thinkers who wish to be clear what is being asserted and how this theory operates and what it achieves. Similarly, in the psychological sciences, if I may just mention one item in passing, the wide acceptance by a great number of people of analytical psychology, that is, various forms of psychoanalysis, I think certainly places a kind of an intellectual duty on the part of students of the operations of the human mind to see exactly what kind of theory this is, what evidence there is for it, whether the assumptions that are being made in it are incoherent, and so on. And finally, to come to a matter that for some strange reason philosophers have tended to neglect, namely the whole area of the social sciences, with which I think many people inclined to have nothing to do on the ground that these really haven't reached the stage of a science. But whether you vote one way or another, it seems to me that there are certain central philosophical questions that are involved in considering the character of the formulations that are made in this domain. Some of them are prima facie statistical in character. Some of them are of a kind which leads many people to wonder whether it is in fact possible to formulate general rules or general laws in the area of human behavior on the ground that there is this well-known phenomena of a self-fulfilling prophecy, that is a self-fulfilling prediction, where making a prediction itself contributes to its own realization, or contrariwise, making a prediction leads to its own defeat. And the examination of logical and epistemological issues that are raised by this situation, I think, certainly demand a good deal of attention. Now, I could go on listing a number of specific problems that are currently under discussion, but instead of doing that, I think it might be more interesting, both to you and I think to me, if I took the remainder of my time to present and to examine one issue that has come to be fairly focal in recent discussions. I'm not quite sure how to formulate this issue. One way of formulating it is the old and familiar problem of of reduction in a science, namely the attempt to explain or to explicate the statements that are made in one branch of science when it offers some kind of a theory in terms of statements that are made on the level of common sense, or vice versa. I mean, this would be one way of formulating the matter. Or another way of formulating it, and the way in which I think I myself would like to attack it this afternoon, is to raise the question as to what the relation is between what one calls the language of theory and the language of observation. Now, this question has been raised, I think, in a rather provocative way by a number of recent writers. For example, it has been raised in a book published a few years ago by Professor Hansen of University of Indiana, Patterns of Discovery. It's been raised by some members of a group around Professor Popper in London, in particular by Professor Feyerabend at the University of Berkeley, in a long article that he's published in the third volume of the Minnesota Studies in the Philosophy of Science. But most recently, it has been raised in a book that has been just published by Professor Thomas Kuhn, also the University of California at Berkeley, in a book called The Structure of Scientific Revolutions. And the way in which I would like to consider this problem is first by telling you a little bit about what Kuhn's position in this book is, and then considering his claims to the extent that time permits. Now, the central claim that all of these writers that I have mentioned, in particular Dr. Kuhn, makes is that what we call the language of observation, the language, not only the phenomenal language which might perhaps describe what is alleged to be immediately presented to the various senses, but certainly the language that one employs in a laboratory when one describes the instruments that one is employing, when one formulates certain familiar so-called laws, often called experimental laws, which assert relations between variables that can be identified or measured by some familiar laboratory procedure. The claim is that the language employed in this context is thoroughly impregnated by a theory, and hence that with the change of theory, the very meaning of the observation statements that one makes become altered. I want to say a little bit more about what is understood by a theory in this connection, but before I do, let me go on to spell out some of the consequences that Dr. Kuhn draws, although he doesn't present this now in a deductive form, from this fundamental claim. One part of his argument in this book, which is based, I think, very largely on historical considerations, is that when, as we often think, one theory, such as the Newtonian theory, is replaced by another, such as physical theory of relativity, and it's replaced because, so we read in textbooks, the new theory can give a better account of certain phenomena than the old theory can, and that if you attempt to use the old theory, Newtonian theory, in this larger domain, it simply gives you incorrect answers, that you accept, the new theory is accepted because of its greater comprehensiveness, that nevertheless, if we think of science as a progressive enterprise, the old theory can be regarded as a limiting case of the new theory. So that in this particular illustration, Newtonian theory holds when the velocities of the bodies with which it's concerned are relatively small compared with the velocity of light. And so if you assume now in the formulation of relativity theory, let me put it now in terms of the special theory, that the relative velocities of bodies is small compared to the velocity of light, then, so that certain terms can be neglected, then you obtain the Newtonian theory as a limiting case. Now, Professor Kuhn denies this, and this carries with it what I think is a terribly important corollary, namely that contrary to our general notions that science is a cumulative enterprise, he makes a distinction between what he calls two periods of science. One that he calls a normal science, where some theory, and following current fashions in philosophical language, Dr. Kuhn calls these paradigms, that certain paradigms have been accepted by a scientific community, and so for a long period, workers in a particular domain of science where this paradigm or this theory is being employed spend their time in spelling out the application of the theory to a variety of domains, solving various kinds of problems which are generated by the theory, and that during this period of what, according to Dr. Kuhn, is essentially kind of a problem-solving period, or even puts it in a fashion that sounds perhaps slightly deprecating, there's a kind of a puzzle-solving period. There might be progress in the sense that many problems, many puzzles that had withstood intellectual attack become resolved. But then, he says, for various reasons, in particular because all sorts of things happen to be discovered which are anomalous from the point of view of the old theory or the old paradigm, in some fashion or other a new paradigm is introduced, and then the problems that had been regarded as serious and meaningful in terms of the old paradigm are simply thrown to the discard, and so that you have essentially a new style of doing science, a concern with different kinds of problems that hitherto had been regarded perhaps even as unscientific, now receive focal attention from workers in the domain, and so that what you have here is essentially perhaps a succession of various periods during which there are, and here I think he certainly adopts a kind of a Wittgensteinian notion, there are various forms of life or ways of looking at things which are essentially incommensurable. And so that rather than thinking of science as an enterprise in which there is progress in a sense that you build upon the work of your predecessors, there are revolutions in science, and during each stable period, once the revolution has been consolidated, and of course the old Tories, they eventually die out, namely those who subscribe to the older views, they are perhaps not convinced, but they die out, until a new group of young Turks appear, and they introduce another style of scientific thought. Now, this is the thesis that Dr. Kuhn submits, which he supports by a variety of quite interesting historical illustration. And before coming to examine the claims, I thought to make sure that I'm not caricaturing his position, I thought I ought to perhaps at least quote a few things, although it might very well be that I'm quoting these out of context. Dr. Kuhn says, as the problems change so often, does the standard that distinguishes a real scientific solution from a mere metaphysical speculation, word game, or mathematical play. The normal scientific tradition, that is, what goes on during a period when one paradigm had been accepted, that emerges from a scientific revolution, is not only incompatible but often incommensurable with that which has gone before. Paradigm changes cause scientists to see the world of their research engagement differently, insofar as their only recourse to that world is through what they see and do. We may want to say that after a revolution, scientists are responding to a different world. And one final quotation. It says, when there's a transfer of allegiance from paradigm to paradigm, this is a conversion experience, not unlike a religious conversion, that cannot be forced. Lifelong resistance, particularly from those whose productive careers have committed them to an older tradition of normal science, is not a violation of scientific standards, but an index to the nature of scientific research. The source of the resistance is the assurance that the older paradigm will ultimately solve all its problems, that nature can be shoved into the box the paradigm provides, while the source of the rebellion is the adoption of a different perspective, a different gestalt upon the course of things, if you like, a different metaphysics, and that these are really incommensurable. Let me stop there as far as the exposition of Dr. Kuhn's point of view is concerned. I know I'm not doing it complete justice, but I think the claim is a very challenging one, and though I do not find all of the claims credible, I found Dr. Kuhn's discussion very challenging, and I also think that he has said some excellent things in the course of his sustained argument. Now, clearly, the central question that we have to first of all consider is, what are we to understand by a paradigm, or what are we to understand by scientific theory? It is quite clear that we are not to understand by scientific theory just any universal statement. For example, that all crows are black. Not just any so-called experimental law. For example, that in an ideal gas, when a temperature is constant, pressure times volume is constant. Because what I think one frequently understands by the word theory, although there's surely no standard usage here. I know, for example, some anthropologists talk about a theory, or say they have a theory, when they venture to make a mild generalization about a particular society which they investigate. But this is not the sense of theory that is at stake here. One thing I think certainly that one would say characterizes theories in the most obvious fashion is that you cannot formulate a theory with the help of a single statement, a single law. And this is kind of a manifest difference between a theory and a a single law. A theory is composed of several statements which are independent of one another. And of course, when I say several statements, I'm well aware that everybody can perform this very simple logical trick of conjoining several statements and have one statement, and so that a theory too could be formulated as a single statement. But this is not a serious criticism, surely, of this way of distinguishing between laws and theories. But I say, quite apart from this, I think that what is so characteristic of at least those intellectual systems that we tend to call theories in the natural sciences, both physical as well as non-physical natural sciences, in some parts of the social sciences, is that these statements, or this set of assumptions, is capable of accounting for a very large variety of qualitatively distinct types of phenomena. And that this is what I would really want to say distinguishes a theory from the sort of thing that one calls an experimental law. The law that I mentioned, Boyle's law, deals simply with certain properties of a gas under certain conditions. On the other hand, if you consider what one calls Newtonian theory, to take an old example, consider the variety of different sorts of things that are at least prima facie qualitatively very different, that it in some sense can make intelligible, can explain, can render an account for. For example, behavior of the tides, the behavior of bodies near the surface of the earth, the motion of the celestial bodies, the strength of beams, the rise of liquids in thin tubes. Well, this is enough, I think, to indicate what a variety of fairly distinct phenomena Newtonian theory can handle. Consider also atomic theory, particularly in one of its forms. It accounts for properties of gases, including the relation of the temperature of a gas to the pressure of a gas. It will account for certain chemical transformations, or at least it claims to account for them. And these are, prima facie at any rate, very distinct kinds of phenomena. Or if you take current quantum theory, the large variety of different sorts of regularities that it can account for is simply fantastic and impressive. And so, by a theory, I want to understand, as I think most people who discuss the kind of question that I'm addressing myself to understand, a body of assumptions which, when they are properly handled, enable us to bring into a systematic order a wide variety of statements about specific regularities, where these regularities appear to be dealing with very different kinds of material, or if you don't want to put in terms of regularities, but in terms of the occurrence of various kinds of events, individual events, the range of application of a theory cuts across certain very obvious divisions of kinds of events, because it deals with a classes of events rather than simply with a single type of event. Now, what is, I think, arresting about these intellectual systems that one calls theories is that though they do deal with such a variety of phenomena, in their explicit formulation, the theories don't mention any of this qualitative diversity. That is, if you think of let's say, kinetic theory of gases, where the fundamental assumptions of the theory are in part the same as those of classical Newtonian mechanics, usually supplemented with some statistical assumptions about the distribution of velocities or positions. Well, there's no mention of the term temperature in this theory. There's no mention in this theory of the term heat. There's no mention of entropy. And these are certainly characteristic terms that one employs in studying the behavior of gases. And so on for quantum theory. And it's, on the face of it, a rather puzzling thing that though a theory apparently has the capacity to deal systematically with such a wide variety of rather distinct things, nevertheless, in the explicit formulation of the theory, at least as it is presented in the normal treatises in subject, the theory mentions none of the predicates that one employs in dealing with this great variety of prima facie very different material. And so the problem is, how can you account for this? How is it possible for a theory to do this? And I suppose one reason why one is puzzled by this is because one recalls what is, in one sense, perhaps simply a logical truism, that if a theory is conceived as explaining any particular events or any laws dealing with a certain range of events, in the sense that the theory enables one, given certain suitable boundary or initial conditions, to deduce those laws or statements about the occurrence of events. That is, that you have here, and I'm assuming that this account is at least approximately a sound account of what happens when a theory is being employed, even though in accepting this as at least an approximately sound account, I must perhaps also note that not everybody does accept this. But assuming that this is so, then I think one reason why one tends to be puzzled by the capacity of the theory to do these wonderful things that a theory can do is that one remembers the simple rule that, well, if you're going to have anything in the conclusion of a deductive argument, then it must already be implicit in the premises. And if you were to write out everything that is really assumed in the premises of a sound argument, then I think one might even go further and say, well, there can be no term that will appear in the conclusion of a sound deduction unless that term appears somewhere in the explicitly formulated premises. And yet, at least in most presentations of the use of theories as ways of explaining, or as principles in terms of which one explains a variety of different laws, it doesn't seem to be the case that all the terms that appear in the conclusion of the argument also appear in the premises as they are normally formulated. Now, this has led, I think, a number of people to distinguish several things in what one calls a theory. And there is, I think, by and large, a general agreement about this among one group of philosophers, even though they might differ in many other ways. What I'm going to say, I think, would represent a core of agreement among perhaps even a majority of philosophers of science, although it is not something that I think would be agreed upon by either Dr. Kuhn or Dr. Feyerabend, or perhaps even Dr. Hansen, whom I mentioned before. Now, what are these three things? Well, the most obvious, when I say three things, of course, what I really mean is that these are elements that one can identify in a theory, not as existing separately side by side, but simply that these are distinctions one can make with respect to any theory in its application as an instrument for explanation or perhaps even prediction. One distinction that one can make is that at the minimum a theory is something one might call an abstract calculus from which, such that accepting certain standard rules of deduction, that you can see what is in some sense entailed or implied by the general assumptions that are made. Now again, I take it it's very familiar that you can, if you like, reformulate even a physical theory in such a way that though you might be using a term like mass normally, or a term like velocity, you can regard these simply as being uninterpreted expressions, and simply on the basis of purely formal rules you can make the derivations. So this is one component or one phase of a theory that one can identify. Then a second point, and this is of course something that has been repeatedly made, has been made certainly very vigorously by at least two members of the Yale faculty, Professor Margenau and Professor Northrop, that in addition to having a theory regarded as being an abstract calculus, you have to have some way of tying up the various points in a theory or various terms in a theory with matters that can be recognized on the basis of some kind of an observational or experimental procedure. That is, that you have to have what I think Professor Margenau calls rules of correspondence, and I like myself to use that expression. Other people call them semantic rules, other people call them coordinating definitions. I think the word definition would be misleading here, even when it's qualified in this way, because the whole point, I think, in introducing rules of correspondence as an indispensable constituent in the articulation of a theory is that the terms that occur in a theory, which one calls theoretical terms, are in point of fact never explicitly defined in terms of distinctions that one makes in context where one makes observation. That is, it's not a term like an electron, for example, or a molecule, or a neutron, or whatnot, that though there must be rules of correspondence, not necessarily between each theoretical term and some expressions that you know how to use in a laboratory or in context of observation, you are not defining the term electron or the term atom. When you do this, you're not defining it because it would make nonsense if you try to replace the term electron by what the rule of correspondence makes it correspond to. That is, unless you do have such rules of correspondence, then you simply have an intellectual calculating machine which seems to be entirely out of connection, out of contact with what we ordinarily refer to as the real world. Now, the third component, which is sometimes neglected and sometimes assimilated to the second one, is the introduction of what is currently called a model or an interpretation for the theory. For example, if one were to do this, which of course is extremely difficult to do, to try to state Newtonian theory in a purely formal way, simply have certain terms like m and x and t without assigning any interpretation to them, or similarly in a kinetic theory of gases do the same kind of a thing, and you might have rules of correspondence which will tell you under what conditions certain expressions are going to be associated, that certain expressions in this formal structure are going to be associated with certain terms that you use in a laboratory, in dealing with matters capable of observation. But in addition to this, of course, we say, well, now look, normally the kinetic theory isn't presented in this formal way. It's presented by way of a model. You say, let's suppose the gas is made up of a very large number of small particles which are moving around in some region with such and such velocities. That is, what you're offering is a model for the formalism which serves as the calculating apparatus. So I would say you have three things: the model, the rules of correspondence, as well as the sheer formalism in terms of which the calculations, or on which the calculations are made. And I say these are distinguishable things because giving rules of correspondence does not mean that you're giving a model or an interpretation. Because, for example, there have been some physicists who have advanced the suggestion that, well, we are not to think of quantum theory as making any statements about anything whatsoever. This is a complicated calculus. You supply some initial information made on the basis of observation. You ask a mathematician who's your slave to make the calculations. Out come some data, some statements which you can then subject to an experimental test, and no interpretation is assigned to all these purely mathematical statements or steps, or to the statements that are made in a process of the mathematical calculation. Such a person would have rules of correspondence, but he would not have a model. Conversely, one can give a model without giving rules of correspondence. That is, if, for example, I were to offer a model for quantum theory, let's suppose now in terms of some conceived kind of a particle that has various kinds of peculiar properties, I still would not know how to use the quantum theory in the sense of knowing how to apply it to experimentally determinable situations. So all three elements, I would argue, are indispensable. Now, to come to an examination of this large claim that Dr. Kuhn has advanced, I think myself that the root of the difficulty, or the root of what I think is the mistake in the argument, is that he, like many others, has committed what I venture to call a literalist fallacy in dealing with a scientific theory, or if you like, a paradigm. And what I mean by literalist fallacy is that you overlook the fact that if you give a model for a theory, that there might be more than one model, and that in point of fact, not every aspect of the model is really relevant in giving some appearance of flesh and blood to the theory. Heinrich Hertz noted this a long time ago in his famous introduction to his mechanics, when he said, well, what we do when we are doing theoretical science is to make symbols of the external world in such a way that the representation of the events in the external world is carried on in a manner so that whatever follows deductively from the symbols corresponds to whatever, as a matter of fact, takes place on the basis of some sort of a causal connection in the order of nature. That this is a minimum requirement that a theory must satisfy. But then he said, of course, there's no unique theory, and moreover, every theory, insofar as it is a system of symbolism, the symbolism itself has certain characteristics which in some way represent the idiosyncrasy of the creator of the theory, and which perhaps cannot rightly be regarded as being representative of anything whatsoever. And so there's first of all the point that if you think of a theory in terms of a model, you have to not think, you must not think of the theory literally in terms of the model. That is, not every feature of the model that helps you to think of the complex relations that are formulated by the theory is really relevant, and as a matter of fact, there might be a whole variety of quite distinct models. But secondly, and I think this is perhaps the more important fallacy that I would like to include under the literalist fallacy, is overlooking the fact that the theory itself has no standing as a part of physical science unless there are rules of correspondence. Let me illustrate what I have in mind. Two examples. One referring to this long paper of Professor Theory-Laden, in which he tries to argue that in the process of developing a theory, and he takes as an example the kinetic theory of gases, where starting out with certain assumptions, deductions are made finally of this kind, that the pressure times the volume is equal to 2/3 of the mean kinetic energy of the molecules. Now, this formula reminds us of something else. It reminds us of the Boyle-Charles law. And then, of course, if you're going to deduce the Boyle-Charles law, you have to say, well, the mean kinetic energy, let's somehow couple this with the notion of temperature as specified by way of some kind of a laboratory procedure. That is, you introduce a rule of correspondence in order to establish a bridge between the theoretical notion of the mean kinetic energy of molecules and something that you can identify by way of some sort of a physical process or experimental process. Now, Dr. Theory-Laden argues, however, that this is not a rule of correspondence, but that you are now defining what you mean by temperature as the mean kinetic energy. Now, of course, you can play this game if you like. You can say, hereafter I will use the word temperature in such a way that it's to be understood as being proportional to the mean kinetic energy of the molecules. And this is what you mean by temperature. But then, if you call this temperature, then the question is, how are you going to apply it in a laboratory, unless you are going to couple this again with some characteristic that you hitherto had called temperature on the basis of some sort of a laboratory procedure. So it seems to me that any attempt to dispense with rules of correspondence leaves the theory up in the air. Take another example from Professor Popper. In his book, Logic of Scientific Discovery, if you read the book, I'm sure you will have been impressed by his attempt to make a sharp distinction between what he calls science and what he calls metaphysics. And he does this on the basis of a criterion that he calls the falsifiability criterion. And this simply means that a statement is a scientific statement if it is capable of being falsified by certain observation statements. Now, it follows immediately from this that a statement which has an existential quantifier, for example, a statement which says there is an element satisfying such and such characteristics. This is not a falsifiable statement, because to falsify it, you would have to establish that no element has such and such characteristic. There's nothing whatsoever which has the characteristic. But since you cannot, on the basis of observation, establish a universal statement, it is not falsifiable in Popper's sense. Now, there's one further consequence that follows from this. If you assume, as many people do, including Dr. Popper, that probability statements in physics are to be construed as assertions about the relative frequency with which certain events occur, And if for no other reason than for the sake of mathematical manipulability, you say, well, now what do you mean by relative frequency? You don't mean relative frequency in a specified set of trials. What you mean is relative frequency in the long run, or to make it perhaps even more precise, the limit of the relative frequency as the series is increased without limit. To say that 1/2 is the limit of the relative frequency of tossing a coin is to make a statement which is, strictly speaking, not falsifiable on the basis of this criterion, and therefore it has to count as a metaphysical statement. And then Professor Popper's much put to it how to allow for metaphysical statements in what he regards as being obviously positive science. And he wants to change this definition and offer something else. Now, I think myself that the solution here is very simple. This notion of probability as a limit of relative frequency is a theoretical notion. And to suppose that you could either confirm or falsify a theoretical statement without giving a rule of correspondence, I think is just absurd. And so that, as a matter of fact, when statisticians and others using probability statements and making applications, making them apply to concrete situations, they always have to associate such probability statements with rules of correspondence. For example, that if an event which has a certain assumed theoretical probability, let's say 1/2, does not occur in a finite number of tosses with a frequency different from 1/2 by not more than some preassigned value, then you will reject then you will simply say the event, the probability is a mistaken one. That is, rules of correspondence of this kind are indispensable. Now, I think, and I must really bring my point to a close, I think that Dr. Kuhn's account of what he calls a scientific revolution and his frequent denial of the cumulative character of science seems to me to be really based on ignoring these rules of correspondence. For example, when he says that you cannot regard Newtonian theory as a limiting case of relativity theory, in one sense, of course, this is perfectly sound. That is, you cannot show to be a limiting case if this means that you can deduce the Newtonian formulas without any supplementary qualifications in the formulations of relativity theory. But clearly, if you are going to apply relativity theory to certain actual situations, you will have to associate the various terms that occur in a particular formulation of relativity theory with certain empirically defined characteristics of empirical bodies. That is, you have to introduce rules of correspondence, and that you will have to do this also for Newtonian theory. And the well-known fact is that in some limited domains, the rules of correspondence that you introduce for both of these theories yield laws that are identically the same. That is, it's in this sense that one can say Newtonian theory is a limiting case, namely it's limiting not in the sense that it is deducible from relativity theory, but limiting in the sense that it holds only in a more restricted domain, provided that suitable rules of correspondence have been introduced. Now, in consequence of this, it seems to me that the claim that science is not cumulative would have to be re-examined. That is, it's hardly disputable, and as a matter of fact, despite the brave front that with which this claim is made in certain parts of the book, then in other parts it becomes fudged a bit because it's admitted that, well, to be sure, there is a kind of a progress going on, because when you replace an old paradigm by a new paradigm, when you replace an old way of looking at things by a new way of looking at things, in point of fact, you are still continuing to use many of the techniques and many of the results that you have achieved at an early state of science. Now, I'd like to perhaps conclude with one rather general observation, which brings me back to my starting point. See, there is this radical thesis underlying Dr. Kuhn's point of view, as well as that of others, is that the terms that appear in these formulations of experimental laws, that they are theory impregnated, and therefore that if you change the theory, the meaning of the experimental laws themselves undergo a change. Now, I think there is something to this. I think undoubtedly we frequently tend to interpret, at least in part, some of the familiar terms employed in a laboratory, or at any rate, we tend to use the language of some currently accepted theory in dealing with some experimental situations. However, this cannot be quite the radical thesis that is claimed to be, because it would certainly be very puzzling how it is, or why it is, that in point of fact theories are abandoned, not simply because somebody finds a particular paradigm aesthetically unsatisfactory, or that it doesn't correspond to his vision on life, but I take it that the normal reason why a theory is abandoned is because there is some anomaly between what the theory asks us to suppose happens from what we observe to happen. And if, however, the language of observation itself were thoroughly impregnated by the theory, it would be difficult to see just how any empirical statement whatsoever could count as counter-evidence for the theory itself. So it seems to me that the connection is not as intimate as is claimed, and as a matter of fact, if I am not completely wrong in stressing the importance and the nature of these rules of correspondence, the rules of correspondence don't impregnate the terms of the laws that are established by experimental procedures with the content of the theory. They simply associate them without altering the meanings of the terms in the theory. So that both on methodological as well as on historical grounds, it seems to me this claim is most dubious. The other point is this, that according to this representation of the nature of the scientific enterprise, one gets a sense that just as there are fashions in literature, fashions in painting, so there are fashions in the way of doing science, and that these differences in gestalt are to be construed not as different ways of trying to find out something about the nature of the world we inhabit, but that they're just simply differences in styles. And as a matter of fact, Dr. Kuhn, in his final chapter, where he tries desperately to give a sense to the notion that, well, there is such a thing as progress in scientific enterprise, he is compelled to say that well, we may have to relinquish the notion, I'm quoting, explicit or implicit, that changes of paradigm carry scientists and those who learn from them closer and closer to the truth. Now, truth is a large question, and I won't propose to discuss it, but I think to abandon the conception that at least one of the motives, one of the grounds for differentiating science from other enterprises is this persistent attempt to find out what things are like, seems to me is being here sacrificed. And though it's certainly debatable, and rightly debatable, whether any particular theory can be said to be true, although I think it is an open question whether, as we look at the succession of theories in the history of science, we can find a kind of a convergence towards some ultimate theory. There doesn't seem to me to be any doubt that if you look at the sequence of stages in development of science where there's an attempt to formulate what I've been calling experimental laws, that there is a convergence, that there is a progression towards a greater scope for experimental laws and a greater precision for them. And that insofar as different theories, different paradigms take their cash value from their ability to systematize, to improve, to suggest experimental laws, to that extent they certainly contribute to the search for truth, and that if it is any reason at all for questioning the approach that I've been stating and trying to indicate the limitations of, that it would convert the history of science not as a conflict between individuals who are all equally committed to the desire to find what the nature of things is, but a conflict between people who have simply different points of view which are not arbitrable. And this, I think, is a caricature of the impulse as well as the justification of the entire scientific enterprise. Thank you.